previously we defined the curves using the vector functions where the r of t comes with some parameter t, which has its 3 components. So the x coordinate is going to give with some function f, the y coordinate is with another function g, and the z coordinates it's coming with another function h of t. So now what we're interested in is to define how the function is curved at some given points, right? For example, here or here or here. So how much it is curved. So this value is called the curvature. Curvature tells us how much the function is curved at some given point. So in order to understand this, what we're going to do is for a given point, we would like to draw a circle so that the borders of the circle are going to match with the graph of the function. So here, if the function is curved a lot, we're going to have a small circle here, and if the curve is not curved a lot, for example here, where the curve is more or less straight, we're going to have a bigger circle. Okay, so here this circle is going to have some radius, and this circle is also going to have some radius r, and we are going to define the curvature as the reciprocal of the radius of the curve, right? So what we want is, so if the curve is straight, more or less, right, then we're going to have a bigger circle, and if I take the reciprocal, it means that the curvature is going to become a smaller value, right? And when the graph is curved a lot, we're going to have a small circle, right? And the radius is small, so when we take its reciprocal, it's going to be a big number, right? And it gives us the value for the curvature bigger than for this point, for example. So we are going to denote the curvature using this curve k, which is called the kappa. And geometrically, conceptually, we're going to define this as 1 over r. So curvature is a measurement of how quickly the curve changes the direction at a given point. So now let's try to define the formula to define a curvature, right? So previously we've learned about the tangent vectors, right? At a given point t, the tangent vector is going to have this direction. This is going to be, if I normalize this, this is going to be a unit tangent vector at some point here, or here, it's going to be another unit tangent vector, another point, and so on. So what we would like to do is we would like to define the curvature as a rate of change of the tangent vector, of the unit tangent vector. So the kappa of t, it's going to be how much the unit tangent vectors changes, right? dt, but not with respect to the parameter, because the parameter is like, you can define different parameters, right? It should be independent from the parameters, but with respect to the length of the curve in some small interval, right? We're going to choose the small interval, and the length of the curve is going to be ds, right? Or the length of the curve between these 2 points is going to be ds, okay, in the model. So we would like to define the curvature as a rate of change of the unit tangent line with respect to the arc length and a small interval of the parameter. So obviously we're going to take its norm here. So please note that we can write down the derivative of the unit tangent vector with respect to the t as derivative of the t with respect to the s multiplied to the derivative of the s with respect to the t according to the chain rule, right? So from here we can find out the dt ds is equal to, so I'm going to find this value is going to be equal to the dt divided to the ds dt, right? So if I substitute this here, it's going to be the kappa, the curvature is going to be defined as dt derivative of the unit tangent vector with respect to the parameter divided to the derivative of the arc length with respect to the parameter t. So obviously we're going to take its norm. So please note that we can write down this as the t prime and its norm divided to, so ds with respect to the t is nothing else as the derivative of the curve at the point t. right? So this is going to be a formula to find the curvature. So by doing some manipulations, we can derive another formula. So please note that the unit tangent vector is obtained by taking the derivative of the curve, right? So the curve is given with some function r, and by normalizing this, right, if I divide this to its length, so take the derivative and divide this to its length in order to get the unit tangent vector. So at the same time, so the norm of the r prime is equal to the ds dt. So from here, what I'm going to do is I'm going to find the r prime. So r prime is going to be equal to the norm of the r prime multiplied to the t. So at the same time, the norm of the r prime is ds dt multiplied to the t, right? And then I'm going to take the derivative of the r one more time. So basically, I would like to find the second derivative of the r. So in order to do this, so this function depends on t and this function depends on t. So if I take the derivative from the multiplication of the two functions, I need to use the multiplication rule, right? So first of all, I'm going to take the derivative of the first part. It's going to be d squared s divided to the t squared. Basically, it's a twice derivative of the s multiplied to the t plus ds dt multiplied to the derivative of the t, right? So please note that when we multiply a vector to itself as a cross product, this is going to be a 0, right? Because when the two vectors are parallel, their cross product are equal to the 0, right? It comes from the formula, so the module of the t to the t, or so u to the v, let's say. So for any two vectors, when we multiply the vector, we have a formula. So u norm multiplied to the v norm multiplied to the sine of the angle between u and v. So when these two vectors are parallel, the sine of angle is going to be 0. So that is why the cross product is equal to the 0. So what I'm going to do is I would like to multiply the r prime to the rt primes as the cross product. So r prime is ds dt. So please note that ds dt is going to be a scalar value, right? Multiplied as the vector t, multiplied as a cross product is a ds squared dt squared multiplied to the t plus ds dt multiplied to the t prime. So if you open up the brackets, so you multiply this vector to this vector as a cross product, right? It's going to be d s dt multiplied to the d squared s dt squared multiplied to the t cross product t, right? Plus ds dt in the square, right? When you multiply this to this, they are the same. Multiplied to the t vector multiplied as a cross product to the t prime vector, right? So please note that when the t vectors are parallel, their cross product is equal to the 0. So that is why when you multiply a vector to itself as the cross product, this is going to be simply 0. So what we have is ds dt in a square multiplied to the t cross product t prime. So now what we're going to do is we're going to take the norm of this vector, okay? So when we take the norm of this vector, it's going to be norm of this vectors, right? So it's going to be ds dt in the square, and the norm of this vector, it's going to be norm of the t cross product is a t prime, right? And we are going to using this formula for the cross product. It's going to be ds dt, so the norm of the t multiplied to the norm of the t prime multiplied to the sine of the angle between them, between t and t prime. So please note that when we take the derivative from the unit tangent vector, it's going to be normal vector, and these two vectors, t and t prime, are going to be perpendicular. So that is why the angle between them is pi over t, so that is why sine of the angle between them is going to be equal to the 1. So at the same time, the length of the unit tangent vector is equal to the 1 because it's a unit vector, right? So here we have a square. So that is why it's going to be ds dt in a square multiplied to the norm of the t prime. Okay, so we've got this equation, right? This is equal, so R cross product is our T primes. Our primes are here. And the norm is equal to this value. From here, we can find the T prime in its norm. That is going to be equal to the R prime cross product R T prime in the norm divided to the ds dt in a square. So please note that R prime in the norm is equal to the ds dt. So that is why we can substitute the ds dt in a square as R prime in the norm in a square. So we can write as R prime cross RT prime divided as R prime in the cross in a square. And please note that kappa, the curvature at some point T, is given as the T prime in the norm, right? Divided to the R prime in the norm. Right? So let us substitute the T prime with this formula which we obtain. That is going to be R prime cross RT prime in its norm. So all of these values are the vector functions divided to the R prime in its norm in the cube. So this is another formula to find the curvature for the given function with the function R at some point T.